early. I want to make sure I start on time to respect your time. Second semester, very, very cool topic, trigonometry. We're going to talk about trig a lot. And, pardon me, we go into a lot of depth about the trig topics. So you're going to go way past SOHCAHTOA that you talked about in geometry and start talking about identities and different things. And trigonometry is one of those topics that you hear from past students, oh, second semester is really hard, it's trigonometry and it's tough. I can honestly tell you that in all the years that I've been teaching this, I've only had one student that after we got done with all the trig said, I just never really got the trig. And it was because she had taken a 2.5-week vacation when we went through the trig in class. So if you're here every day and you're following along with what we're doing, you're able to ask and answer questions, trig is not going to be super hard for you. But you have to be here and you have to be present. And by being present, I don't mean that your icon is just staring at me there. I mean that you're involved in the lesson, that you're asking and answering questions as we go through it. That's been proven to help people learn. Our brain's a marvelous little machine, but it needs our help. Everything that we learn in class goes right behind our forehead into our short-term memory. And then we have to do the practice, and we have to do it right to move that information into our long-term memory, our hippocampus. And so there has to be follow-through. Now, I don't worry too much about that at the pre-calculus level because that's why most of you are here, is because you have that follow-through. But make sure that you're doing everything that you need to do each and every day. Now, those of you that didn't have me first semester, when you look at the due dates for the homework, remember that sometimes I'll have to push those back because sometimes we don't make it through all the material that we need to for you to do the assignment. And if that's the case, I'm aware of it, and even if it says that, the due date is past and it's late, I give full credit for those assignments. It's just one of those things where I want to spend most of my time teaching you the material and not be so worried about, okay, did we meet a due date for this, that, or the other thing. Also know that the time on them is always going to be 1:30 p.m. for the next day. And that's because really you should be doing your homework assignments in the evening. The brain, like I said, is a marvelous little machine. And if you come back to a topic that you've learned within 8 to 12 hours, that's how we can get that information into your long-term memory. So try and use that. And then the reason that I put the 1:30 p.m. deadline on the homework is because that's my prep. Right after 1:30, that's my prep, and that's the time when I'll be putting homework into the system. So if anything else, I guess I'd just call that, our normal routine. If anything else comes up, just make sure you ask. Don't be afraid to hang on a little bit after everybody else leaves and ask a question every now and then. All right, away we go with trig. So chapter 4 is trigonometric functions. And when the motion of an object causes air molecules to vibrate, we hear a sound. We measure sound according to its pitch and loudness, which are attributes associated with the frequency and amplitude of sound waves. As we shall see, it is the branch of mathematics called trigonometry that enables us to analyze waves of all kinds. Indeed, that is only one application of this powerful analytical tool. And we have a lot of applications we'll talk about later. One of the coolest that I've ever seen put into development is going to be when you are at recycling centers. Most recycling centers use magnet to get any kind of metals out before they'll take anything to the landfill. But aluminum does not attach with magnets. And so they worked out a system so that what they do is they hit the metals with sound waves, and aluminum will ping up in the air when it's hit by a certain sound wave. And then they would catch the aluminum cans and things to recycle them in the net. And that takes the study of the sound waves to make that happen. So very cool stuff that's been going on with sound waves. One of the others that, if you're interested in zoological things at all, is elephants. For years and years, people have believed that elephants actually speak to one another, but that it's on a frequency that we can't hear. And so right now, scientists are trying to figure out, what is this frequency that elephants talk to each other with? And hopefully, eventually, we'll know what on earth those elephants are doing. Because they're supposed to be very, very smart animals, and their migration patterns are very well thought out. So all kinds of areas that trig comes in handy. What to expect in Chapter 4. Trigonometric functions describe the ratio of two sides of a right triangle, regardless of the size of the triangle. This goes back to, my blue marker always takes a minute to wake up. SOHCAHTOA, back from geometry. So you learned that little mnemonic device to remind you that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Those are little fractions that in math are called ratios that describe what's happening in the relationship between two sides of that triangle. So that part we already know. The compilation of these numbers allowed the progression of many topics in mathematics, absolutely. Who would have thought that the first trigonometry tables would help enable us to store sound waves digitally on a compact disk? So obviously when they were building the pyramids, they didn't foresee that anything was going to be used fancy like that to make sure that we can hear our music on a computer, but that's in actuality what happened. The study of trigonometry is both historic and essential as we progress through calculus. You use it a lot in calculus. Angles and their measures. I'll spend quite a bit of time on that today. Trigonometric functions of acute angles. Trigonometry extended, talking about the unit circle, circular functions. Graphs of sine and cosine. Those are called sinusoids. Graphs of tangent, cotangent, secant, and cosecant. We're going to look at all the graphs. Again, only sine and cosine waves are referred to as the sinusoids. Inverse trigonometric functions, and then solving problems with trigonometry. All of these things are part of Chapter 4. And there's so much great trig in Chapter 4 that, of course, we have to section this up into two different tests. So the first test will cover sections 4.1 to 4.3, and then the second will get the back half of this. And we've learned that about our pre-calculus book as well, that there's a ton of different things that they put in each section, and often we can only give you a test on, well, 3 or 4 of them at a time, otherwise the test would be too long. So kind of a math geek, well, okay, not kind of. I'm a math geek, and I love math history. So this is really cool here, talking about Hipparchus of Nicaea from 190 to 120 BC. Hipparchus of Nicaea, the father of trigonometry, compiled the first trigonometric tables to simplify the study of astronomy more than 2,000 years ago. They wanted to sail the seas, but people could easily get lost on the oceans because they were so vast. So they would use the stars to guide them where they needed to go. Today, that same mathematics enables us to store sound waves digitally on a compact disk. Hipparchus wrote during the 2nd century BC, but he was not the first mathematician to actually do trigonometry. Greek mathematicians like Hippocrates of Koi and Eratosthenes of Cyrene had paved the way for using triangle ratios in astronomy. And those same triangle ratios have been used by Egyptians, Babylonian engineers at least 4,000 years earlier. The term trigonometry itself emerged in the 16th century. It is Greek, tri meaning 3, gonos meaning side, and metros meaning measure. So they put those things together and you've got trigonometry. The Babylonians are thought to have developed the first number system, which was a base 60 system. They lived in Mesopotamia, which is thought to be a portion of modern-day Iraq. So, what does that mean, a base 60 system? Well, I'm going to tell you about that in terms of what our system is. We have a base 10 system. So when we start counting, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then we start to repeat. 10 plus 1 is 11. 10 plus 2 is 12. You keep that tens position the same. Their system was based on 60 separate markings. So you had to go 60 different digits until you saw any repetition, which makes you go, what were they thinking? 60? That's too many for any normal person. Well, first of all, not every normal person got to study math back then. It was people that were wealthy and could afford an education, didn't have to be out finding food because they had other people to do that for them. So they picked 60, and there's an explanation here in a little bit of why they used the numbers that they did. So if they have a base 60 system, why did they decide that a circle would be 360 degrees? Where did that come from? Well, truly, they just liked it because you could divide it by lots of stuff. I mean, that's exactly why they picked it. It had a lot of factors. So the idea of dividing a circle into 360 equal pieces dates back to the sexagesimal system, which is that 60-based counting system of the ancient Sumerians. The appeal of 60 was that it was evenly divisible by so many numbers. It had a lot of factors. 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. So you could work with it with a lot of math, and that's what they wanted. Early astronomical calculations wedded the sexagesimal system to circles, and the rest is history. Now, this was the first way, the most historic way that circles were ever thought of, was the 360 degrees. Is it the best way? And the answer is no. Obviously, there has been more math developed since thousands of years BC. So what we have to do is say, yeah, this was a good way to learn. It was good in geometry that you got an idea of this 360 degrees, but what does that have to do with circles? You know, how do those two things come together? And we're going to talk about that a bit today. So in section 4.1, angles and their measures, we're going to be able to work with the DMS system, and that is degrees, minutes, and seconds. So, somebody said this degree thing of 360, it's great, but it's not the most accurate thing in the world. So, they decided, well, let's break it up a little further. Let's think of it as if it were, a clock, and let's talk about degrees, minutes, and seconds, and we'll go through some of that information. We're going to draw some angles in standard position, find coterminal and reference angles, make conversions from degrees to radians and vice versa, because here is our exposure to something that is much more accurate than degrees, and that's going to be radians. Finding arc length, make connections between angular and linear motion. Yeah, we're not going to get to all that today. We've got 4 days set aside for this section, so what we have to do is just take what we can each day and build on it and go from there. Alrighty, away we go. The blank variable in a trigonometric function is an angle measure. That's the input. We want to use those angle measures to find the ratio of two sides of a triangle. The output is a real number. That's how we have those buttons on our calculator that we can push that have sine, cosine, and tangent on them, and a number will be cranked out. Used to be really thick tables in the back of textbooks before calculators came along that had all those trig values in there. So an immediate problem arises based on our choice of measurement. Should we use degrees or radians? Well, degrees have absolutely no mathematical relationship whatsoever to linear units. None. So if you start talking about arc length and you're using degrees, those are two separate measuring systems. And that's the reason that it doesn't come out as accurate as we would like it to. So there are 360 degrees in a circle of radius 1. And we have to remember the only reason that was picked was because it was divisible by a lot of nice numbers, a lot of nice integers. However, There is no explanation for how the 360 actually relates to the 1. So radius is a length of 1. What does that have to do with 360 degrees? And the answer is absolutely nothing. They were not thinking that far ahead. They just wanted to be able to find stuff when they were out on the ocean. And they did it the best way that they could at that time. So, no explanation for how the 360 relates to the 1. Degrees are an entirely different unit of measure. So we have a little right triangle here, and we can see that it's set up so that we have theta right here in the corner as an angle. And we remember all of those labels that we had back in geometry with SOHCAHTOA. And as far away as you can get from it, in fact, it's not even touching your angle, is going to be the opposite side. And then the side that it's touching is going to be the adjacent. And the hypotenuse, yes, it is the longest side, but when our triangles get kind of small, we want to remember the true definition is the hypotenuse is opposite the right angle. And we can use the trig to do what's called solving the triangle. If we have enough information, we can find every little piece that we could possibly need on that triangle, all 3 sides and all 3 angles. Now, the next triangle over here is showing us, here's our angle, here's the arc length. How are those two things related? Well, with degrees, they're not. Now, let's see what happens if we start thinking in terms of radians. So, down below, in the above diagram, the ratio of S to H in the right triangle is independent of the size of the triangle. As one of these sides gets bigger, this hypotenuse would get bigger because the angles would stay the same. Those were called similar triangles when you studied them in geometry. So remember similar triangles from geometry. In this diagram, S is half a chord in a circle of radius h. So let's finish that up. The radius is h and S is half a chord. And let's just draw, obviously this is not going to be perfectly to scale, a circle that would do that. They're saying if we were to connect this up like so, we could have a full, well, it'd be actually 2S in this situation, but we could have a chord. Now, how does that help us? Well, S is half a chord in a circle of radius h and central angle of the circle intercepting a circular arc of length A. The arc determines the angle leading to radian measure. So here's what they're saying. Forget about degrees. Instead, think about this angle called the central angle. And we want to think, how does this give us a radian? And I want to give you your first exposure to radian here. A radian is determined because we take the radius of a circle and we draw an arc length that is equal to that radius. Now, obviously, it doesn't look that way in my picture here. But that is how you get 1 radian of a circle. Your radius equals your arc length, and that cuts out 1 radian of a circle. They're both lengths. Radius is a length, arc length is a length, and so they're in the same units. And that's what makes radians so much more exact than degrees. So again, they're introducing us to some language that you did have back in geometry, but you maybe forgot. A central angle, an arc. They're talking about a chord, and a chord, again, is a segment that has its endpoints on the outside of the circle. And we're just getting back into talking a little bit about, geometry terms that you've had before. The arc determines the angle, and that leads to radian measure. You're going to feel most comfortable with talk about degrees today. But I am also going to try to give you some exposure today to radians, because the more exposure you have to it, the more comfortable you're going to become with it. So, a degree is represented by the little symbol for degrees. Now, this is really important. Remember, we are not just going to work with degrees this semester. So if you're using degrees, you have to have that degree symbol. Anything else is assumed to be in radians, because radians don't have a label. So a degree represented by the symbol, little degree bubble there, is a unit of angle measure equal to 1/180th of a straight angle. Because back in geometry, you learned straight lines are 180 degrees. And that makes perfect sense, because that would be halfway around a circle. So you'd have your semicircle length. In the DMS, degrees, minutes, and seconds system of angular measure, each degree is subdivided into 60 minutes. And it does help to think about the clock. Now that's going to be denoted by one little apostrophe when we label that for minutes. And each minute is subdivided into 60 seconds. So like I said, degrees, minutes, and seconds, it's best to just think of the clock when you're doing that. So there are 60 minutes as you go around the clock. 360 degrees, 60 minutes, and then you subdivide that again into 60 seconds. Few people have their cameras on, so I'm just making sure that everybody has enough time to write down what they need here. All right, away we go. Example 1, working with DMS measure, so degrees, minutes, and seconds. Convert 37.425 to degrees, minutes, and seconds. Well, pretty obviously, we've got 37 degrees. But then we have a portion of degrees, and we want to make that into minutes and seconds. So we have 0.425, and I want to convert that into minutes. Well, 360 degrees is equal to 60 minutes. So I'm going to have to multiply that by 60 to figure out how many minutes I actually have. I have 25.5 minutes. And that's one apostrophe. But then I realized, well, I could still go on. I still have a decimal portion of my minutes here. So what I should do is find my 37 degrees, 25 minutes, but find 0.5 of how many seconds there are. And again, 60 seconds. So 0.5 of 60 is going to be 30. And we get the little apostrophe for that piece. So 37.425 in degrees, minutes, and seconds is 37 degrees, 25 minutes, and 30 seconds. Now that's working forwards, taking degrees and changing that into degrees, minutes, and seconds. This time we have to work backwards. It says we're going to do the converting, and they gave us degrees, minutes, and seconds. So this will be 42, and I know the 24 was out of 60, but now I have to think for a second. If all of this is supposed to be in degrees, how many seconds are actually in a degree? Well, let's see. There were 60 minutes, and then there were 60 seconds in each of those 60 minutes. That makes for 3,600 seconds. And you can think of that as, an hour's worth of seconds. So if we need this back in degrees, and usually the reason for that is going to be finishing up word problems, we're going to have to figure out what all that mess is. So, grab my little notes here so I'm making sure I'm punching in all the numbers we have there. And we had 42 plus parentheses 24 divided by 60 parentheses plus parentheses 36 divided by 3,600. So there it is as a decimal, 42.41. And definitely we need that label on there. Remember what we were supposed to achieve. We were supposed to take this into degrees. So like I mentioned, if you just think of the DMS system as using the clock, you'll be just fine. Degrees, minutes, and seconds. Now, is that what they did way back when? No, they didn't. They were mostly just using degrees. Later on, they tried to get a little more specific, and then, yes, they did degrees, minutes, and seconds. So word problems are always written the old way, the way that they used to use for astronomy for the seas. In navigation, the course or bearing of an object is sometimes given as the angle of a line of travel measured clockwise from due north. So this is huge. The word bearing. When we hear that in a problem, we have to remember, oh, that's special. That was back when they figured out everything from the North Star. And that's really what they did. They used the North Star as their guide. So when they say they were traveling at 155 degrees, that means they were traveling 155 degrees clockwise from due north. From due north. And if you remember your geometry, that's definitely not the way we would draw 155 degrees mathematically. But if we're reading a word problem and they use bearing, we have to remember that's special. That's something that's very ancient, that's been done forever. So, the course of a fishing boat bearing 155 degrees out of Gloucester, right there. Now, we know that's not the way we're supposed to draw them if we remember anything about our geometry. So, review from geometry. Definition. An angle in standard position has its initial ray on the positive x-axis. So, mathematically, this angle looks very different from what we see in that picture for the word problem. Because when we start an angle, mathematically, it's supposed to start on the positive x-axis, and that's called the initial ray. The terminal ray may land anywhere. A counterclockwise rotation is a positive angle. So it's actually going in the opposite direction that it was going before when we saw that word problem. So a counterclockwise rotation will result in a positive angle. This is why the quadrants are numbered the way they are. It's all very European. Remember, ancient civilizations. So it's backwards of what we would think today because we have to go counterclockwise. So we would say for this angle, well, there's 90 degrees. Now, how much farther do I need to go to get 155? And that would be an additional 65 degrees. And that would give us what's called the terminal side of that angle. Note, very different angles. So we have to be very careful with word problems. If we find the word bearing, then we have to know that that was from due north. And it was going clockwise from due north. Mathematically, very different picture. A clockwise rotation is actually a negative angle mathematically. And we use such Greek letters as theta. This is actually supposed to be pronounced pi. But because I don't want anybody to confuse it with pi, I'm going to call it phi. So phi, alpha, beta, and omega. And most of the time, books will stick with theta, but the Greek letters are something that have been used for a long time to talk about those angles. So a clockwise rotation is actually going to be negative in the mathematical system. Learn a little Greek. The pictures below show some angles in standard position. What are some plausible angle measures for each? All right. Well, we know mathematically they start on the positive x-axis. And this little arrow is something we have to draw when we're drawing angles because we have to show people, is this going clockwise or is it going counterclockwise? So this one is going counterclockwise, and there's the terminal side. Now, it says plausible because we don't want to get a protractor out. We want to look at it and say, you know what, that looks about halfway up to y, the positive y-axis. I think that's 45 degrees. Now that, I'm guessing, everybody could have done. Here's what I want you to start thinking instead. I want you to start thinking radians. Every circle has 2 pi radians. Now, again, we don't normally label radians. I'm going to this time because I want everybody to remember that in their notes. So here's what that means. That means from positive x-axis to negative x-axis, you have 1 pi. And then to go all the way around, you get another pi. And now you've traveled 2 pi radians. So I think, well, how can I represent 45 degrees in terms of pi? I look at the top, quadrants 1 and 2, and I think, well, if that's 1 pi, I could fit 4 of these angles in there because they're 45 degrees apiece. So that would be pi over 4. And that would be the radian measure for 45 degrees, pi over 4. Now, some people like to think of it in terms of translation. You've learned everything about degrees, so some people would do this. This is 180 degrees up here. How many times does 45 go into 180? Oh, it goes in there 4 times. And that will give them pi over 4. Either way, we have to start being exposed to that and thinking about that and how it works. Because degrees is something we should already have figured out. Here is our x-axis. This time our angle is going to go clockwise. And that means we need a negative. Because remember, it's all very European, and going clockwise is actually a negative measurement. And then I think, okay, that looks about halfway again through quadrant 2. So I would say this looks like 45 degrees right here, that little angle right there. And later on, we're going to learn the special name for that angle is a reference angle. But right now, what I want to do is come up with the whole measurement. From the positive x-axis all the way over to that blue, and let me make it red right now, red terminal side, how many degrees am I talking about? Well, I would have 180 to go all the way across, and then I'd have to add another 45. Which is 225. Now, in terms of radians, I think to myself, well, this would be 1 pi going all the way across. But 45 degrees is still going to be pi over 4. So what I'd have to do is get a common denominator here. And that's pi over 1 right now. so I'd need to multiply by a 4 on the top and the bottom. So I'd get 4 pi plus 1 pi, which is 5 pi, a negative 5 pi over 4. So radians are more fraction thinking. And again, much more accurate for what we need. All right, going to the third one. There's my initial side. I follow the arc. 180 degrees, 360 degrees, and oh, yep, it looks like another 45 again. And this time it's going counterclockwise, so that will be positive 405 degrees. I want you to take a second and see if you can figure out the radians. And then let's see if somebody's willing to unmute and tell us what they had. It is. Thank you. 9 pi over 4. When you've gone all the way around, you've gone 2 pi. And again, they keep sticking with that 45-degree angle for us, which would be pi over 4. Get a common denominator of 4 by multiplying on the top and the bottom by 4. And 8 pi plus 1 pi would be 9 pi over 4. So 405 degrees, or 9 pi over 4. The last one over here, again, think about that positive x-axis. Looking at my arc to see, is this going counterclockwise so it's positive, or clockwise so it's negative? It is going counterclockwise. It's going to be positive. And then we think, all right, there is 1 pi, 2 pi, 3 pi, and a little bit more for the radian measure. For degrees, we'd think, well, there's 180, 360, got to go again, so I'm going to have to add another 180, and looks like they went halfway again for another 45. So, grand total of 585 degrees. And make sure you put your little bubble on there. That, I'm pretty sure you could have done all by yourself. The 3 pi, we know we still have to add pi over 4. Hopefully some of you are like, I don't even need to think the common denominator thing anymore. I know this will be 12. 12 plus 1 gives me 13. But doesn't hurt to show the steps. So 12 pi plus 1 pi, 13 pi over 4. So like I said, I want to give you the exposure to the radians as we're talking about the degrees, because I'm absolutely certain you are solid as far as degrees go, but you have not had a lot of exposure to radians in the past. Alrighty, this says draw the following angles in standard position. Show the arc between the initial and terminal ray. So they should look like the ones that we just saw. So here's our initial side. Should put my little XYs on all this. And we are to draw 190 degrees. So that's going to be counterclockwise because it's positive. There's 90, 180, and I'd have to go just 10 degrees more. And because it's not going to be to scale, I mean, this is way more than 10 degrees, I would just label 10 degrees right there. And again, that helps us learn about reference angles, because that would actually be a 10-degree reference angle for 190 degrees. Negative 276. We see the negative, we should be thinking clockwise. Let's see, we've got 90, 180, 270, and I need just 6 degrees more, which again, really hard to draw. So I would just label that 6 degrees. Now that's not a reference angle, but it helps us figure out what's going on with that drawing. Next one, we have negative 91 degrees for phi. And so we'd go negative, which is clockwise, and we'd have to go 1 degree, which again, I'm overemphasizing that. So I want to make sure that I have that label of 1 degrees in there. 629 degrees. Well, let's see, that's going to go more than once around, and we'd want to know how much more than once around. So we'd subtract 360 to figure that out. And that would give us 269 degrees. So alpha here is 629. And get my x's and y's labeled. Positive x-axis. It's a positive angle. It's going to go counterclockwise. 180, 360, and then I have to go another 269 degrees. 90, 180, but not all the way down. We'd be short 1 degree. Now, something interesting just happened. If we take a look at this, we realize C and D, angles phi and alpha, give us the exact same terminal side. That happens. The terminal sides match up. 1,822. Wow. How am I supposed to know where that's going to land? Well, first we'd want to know how many full rotations. So we'd want to take 1,822 and divide that by 360 and find out how many full rotations are we talking about here. And we get 5.06111111. So I'll write that to 3 decimal places. So that means there are 5 full rotations. But again, I care about where it lands. So what I would want to do is take 1822 minus those 5 full rotations and see what's left. So 1822 minus parentheses 5 times 360. So after 5 rotations, there's going to be a little 22 degrees left for us to draw. So you might want to make these pretty tight into the center here. It is positive, so counterclockwise. 1, 2, 3, 4, 5, and 22 more degrees. Right there. And again, it's exaggerated. It looks more like 45 degrees than 22, and that's why it's important that we're labeling. All right. F. Okay, Omega, we're ready for you. We know how to figure out how many full rotations. We're going to divide. And we'll see what we get. So negative 160.086. So what we want to do this time is say, all right, I've got negative 57,631, but now I'm going to add those 160 rotations. Of 360 degrees. because I want to know the difference between the two. And it is a negative 31 degrees. Well, how on earth am I supposed to show 160 rotations? Well, we're going to have to make a little key. Like when you look at old maps, and we're going to have to tell people, you know what, I'm just going to make a dashed line here, and that dashed line equals 160 rotations. Because we definitely can't fit 160 rotations on there. Not going to happen. So we have our negative, which means we have to go clockwise, and we're going to show dashed, dotted, whatever it takes to get that 160 rotations, and then we need to go another 31 degrees. And make sure you have your arrow on there showing that that's going to be going clockwise this time because it was negative. So these examples really could have been something right out of your geometry book. You know, they're about degrees, figuring out how to represent angles with our normal mathematical procedures, with the initial side on the positive x-axis and the terminal side wherever it happens to land. In example 3, we saw that our two angles, phi at negative 91 and alpha at 629, they shared a terminal ray. They landed in the same place. Although we can't say that those angles are equal because they're not. They are coterminal. When angles land with their terminal side in exactly the same place, they're called coterminal. So two angles are coterminal with each other if they share a terminal ray. In general, any given angle, theta, its coterminal angles are given by theta coterminal, little subscript there of COT, and it comes from adding and subtracting multiples of 360 because it would land in the exact same place. So theta plus 360n, where n is the set of z, which remember that's been a long time ago since we talked about that, is a set of integers. So this one says, if theta is 465, find all the angles that would be coterminal with it for theta from negative 1,000 degrees to 1,000 degrees. So here's our 465. Well, we might as well start by looking at the smaller ones. So we'll subtract 360, and we'll just keep subtracting 360 until we reach that negative 1,000. So 465 minus 360 degrees is 105. Minus 360 degrees again. Oh, I think we still got a minute here. Negative 255. Minus 360 again. Negative 615. Minus 360 again. Negative 975. And of course, if we subtracted more, then we'd be outside that range of negative 1,000. And then we can go ahead and go back and say, all right, well, what if we add the 360? So 465 plus 360, 825. And of course, if we add another 360 to that, we're going to be outside that range of negative 1,000 to 1,000. So theta coterminal. Let's write them down and let's put them in order. We had negative 975 we had negative 615. We had negative 255. And then we had 105 and 825. So those are the angles between negative 1,000 and 1,000 that will have the exact same coterminal terminal ray. And that's where we're going to have to quit for today. And I know it's disappointing, but you won't be able to do a whole lot of homework. So it is a worksheet in that black digital file called, it actually says 4-1 Day 1 worksheet, but it's going to have 13-2 labeled on the front of it. Let's see if I can get that up here. Nope. So in the black file, had it for a second, and then it went. Right here. Worksheet section 4-1 Day 1 labeled 13-2. You won't get far, but at least you'll get a little bit done. Start to lock it into your memory. Have a great day, everybody. Thanks for hanging in there.